Good morning. We're here. We're going to give it another minute to let other participants join in. We'll be right back with you. Good morning and welcome to the Technical Methods Workshop for the 2025 Central Florida Water Initiative, or CFWI, Regional Water Supply Plan. My name is Callie Register and I'm the Regional Water Supply Planning Coordinator with St. Johns River Water Management District. I'm here today with colleagues from St. John's, South Florida, and Southwest Florida Water Management Districts to discuss the ongoing work for the 2025 Regional Water Supply Plan. This workshop presentation and audio will be recorded and made available on the CFWI website. Sorry about that. The objective of today's meeting is to present the technical data and modeling tools used in support of the 2025 plan. We will not be presenting any results today, but we'll be going through the technical methods. First, I'll provide an overview of the CFWI Regional Water Supply Plan and recap work done so far in the process. We'll then hear from the technical leads on methods used to update the analyses. Pete Kwiatkowski will present the hydrologic analysis. Doug Leeper will present on minimum flows and minimum water levels. And then Kim Holtzwart will present the environmental measures methods. There will be time for questions or comments at the end of each speaker's presentation, and we will provide a slide with instructions on how to do so at that time. Stacy. Excuse our I will start with an overview of the regional water supply process in support of the 2025 CFWI Regional Water Supply Plan. The statutory requirements for regional water supply plans include population and water demand projections for a 20-year planning period, an assessment of available water supplies to determine whether current and future demands can be met with fresh groundwater without harming Florida's natural systems, and if not, identification of management strategies, water conservation, and alternative water supply projects to meet future needs. Plans must also identify project funding options, and the plans must be updated every 5 years. Given that the first CFWI Regional Water Supply Plan came out in 2015, we have the benefit of not starting from scratch for the 2025 plan, and will build on the work done for the 2015 and 2020 plans. To date, we have updated the historic and projected population, water use, and water demand projections for the 2025 CFWI Regional Water Supply Plan. The updated water use data will be used as inputs to the groundwater flow model. Using the updated groundwater model results, the districts will be able to verify the identification of existing and reasonably anticipated groundwater sources. In addition, we will also update our strategies included in the 2020 plan, such as the water supply and water resource development options and water conservation potential to meet the future water demands identified while protecting the water resources and related natural systems. The goal is to complete the 2025 CFWI Regional Water Supply Plan according to the timeline I will provide later during this presentation. The 2025 plan, which we began work on in 2021, is the second 5-year update to the 2015 CFWI Regional Water Supply Plan. The 2015 and 2020 CFWI Regional Water Supply Plans were developed in coordination with South Florida Water Management District, St. Johns River Water Management District, and Southwest Florida Water Management District, the Florida Department of Environmental Protection, Florida Department of Agriculture and Consumer Services, other agencies, and stakeholders. This 2025 plan is occurring in a streamlined manner because of processes and procedures already developed, documented, and agreed upon previously during the first 2 regional water supply plans, which provided an established framework for future updates. The Central Florida Water Initiative is a collaborative water supply planning effort covering an area including portions of 3 water management districts and 5 counties: Orange, Osceola, Seminole, Polk, and Southern Lake. There are 50 local governments in our area, with the city of Orlando being the largest. Approximately 3.8 million people call Central Florida home, and it is continuing to expand rapidly. As we know, Central Florida is an international tourist destination with Disney World, Universal Studios, and many more attractions. There is also a major agricultural industry with about 122,000 agricultural acres under irrigation, primarily in citrus, followed by sod. Over 56% of the agricultural demand is in the Southwest Florida Water Management District, while about 22% occurs in each of the other 2 water management districts. There are many natural systems in this region that are water dependent, including springs, wetlands, and numerous lakes. The CFWI planning area projections are summarized here and were previously presented at a public meeting last October. The population and demand projections were developed with input from many external stakeholders through a process that started with a kickoff meeting in January 2022. As shown, the 2025 CFWI Regional Water Supply Plan population is projected to have a 40% increase to 4.7 million people by 2045. Irrigated agricultural acreage and water demand is projected to decrease slightly, and total water demand in the planning area is projected to increase by 41% to 903 million gallons a day by 2045. This slide shows the historic water use and projected water demand in the CFWI planning area. Our water demands are trending with historic water use considering the anticipated population growth. From 2015 to 2020, the area had an increase in population of approximately 450,000 people. This can be attributed to not only growth, but the estimates of population provided by the 2020 U.S. Census. This area's efficient use of reclaimed water and implementation of conservation has contributed to the trends we are seeing and is expected to continue to offset the groundwater demands of the CFWI planning area. Groundwater availability is a sustainable quantity of traditional groundwater sources that can be used without causing unacceptable impacts to water resources or associated natural systems. Groundwater availability in the CFWI planning area was established in the 2020 plan based on minimum flows and minimum water levels, MFLs, water quality, and lakes, wetlands, and springs criteria. The CFWI rule became effective in 2021, and currently there are 5 new MFLs under development and 10 MFLs under reevaluation in the planning area. The adopted rule is being implemented, and there are several alternative water supply projects currently being planned and constructed. The The modeling conducted during the 2020 plan process indicated that as groundwater withdrawals increased, there was a corresponding predicted increase in hydrologic stress on environmental systems. Groundwater withdrawal impacts can generally be characterized by the spatial extent and magnitude of the impacts based on areas of environmental sensitivity. Primary areas or features that appear to be more susceptible to the effects of groundwater withdrawals and thus may limit additional groundwater development are shown and include the Wekiwa Springs Wekiwa River System, West Seminole County, West Orange County, South Lake County, East Osceola County, the Lake Wales Ridge, Upper Peace River Basin, and Central Polk County north of I-4. The planning level groundwater availability assessment completed during the 2020 Regional Water Supply Plan update indicated that further development of fresh groundwater withdrawals beyond 760 million gallons per day, as indicated by the yellow dashed line, trips minimum flows and minimum water levels within the St. Johns River Water Management District. Above 760 million gallons per day, two outstanding Florida springs, Wekiwa and Rock Springs, minimum flows and water levels will not be met, and additional wetland acreage is predicted to be stressed. Based on the 2020 analysis, it was anticipated that we could exceed our fresh groundwater availability by 2025. To help meet the needs of the projected 2045 groundwater demand of 856 million gallons per day, project options and conservation potential will be evaluated and updated. Shown here are the 2020 Regional Water Supply Plan identified alternative water supply project options in the amount of 532 million gallons per day and conservation potential in the amount of 50 million gallons per day. The project options and conservation will be updated for the 2025 plan. The updated groundwater demand and allocations shown here have not changed much since the 2020 plan. It should also be noted that MFLs for Wekiwa Basin and other MFL water bodies are currently under reevaluation and may alter the groundwater availability in the future. In the meantime, we are continuing to monitor these systems and wetlands. It appears likely that a prevention and recovery strategy will be needed for some of the MFLs in the area, thus requiring implementation of specific projects and management strategies. Project options for water supply and water resource development include alternative or non-traditional water sources such as brackish groundwater, surface water, stormwater, reclaimed water, aquifer storage and recovery wells and reservoirs. To date, in addition to various stakeholder meetings, we have had a public outreach meeting that occurred in October 2023, as well as today's technical methods workshop. The schedule moving forward from today includes a steering committee public workshop in October 2024, where we will present results and the draft plan conclusions. The three districts will present overviews to their governing boards in February and March of 2025 regarding the draft CFWI Regional Water Supply Plan. The draft plan will then be posted mid-March for public review and comment. A steering committee public workshop will be held in April 2025 to discuss the draft plan and answer any questions. The public comment period will be open for 60 calendar days after posting, with anticipated comment period closing mid-May 2025. A steering committee public workshop will be held in October 2025 to provide an overview of comments received and any substantial changes made to the draft final 2025 plan. The three districts will present the draft final plan to their governing boards in November 2025. After all approvals, the final 2025 CFWI Regional Water Supply Plan will be posted to cfwiwater.com in December 2025. At this time, we'll take any questions regarding the process. You will notice on this slide directions how to raise your hand in Zoom. If you're participating via Zoom, please use the raise hand feature and then remember to unmute yourself. If you're participating via phone, *9 raises your hand, *6 mutes and unmutes your line. When you are called upon, please state your full name and affiliation prior to providing comments and/or questions. . Does not appear that we have any questions. We'll now close the questions for this portion of the presentation. Next up is Pete Kwiatkowski.
Okay, good morning, everyone. My name is Pete Kwiatkowski. I'm with South Florida Water Management District, and I'm going to be discussing our approach in terms of a hydrologic assessment that will be used to support the water supply plan. Okay, what I'm going to be covering today is the purpose of the modeling that we're going to be doing. Give a brief overview of the hydrogeology and hydrology of Central Florida. Next, I'll be discussing the groundwater flow model that we are going to be using for this effort. It's a very long name. It's called the East Central Florida Transient Expanded Model, and we just call it ECFTX version 2.0, and even that acronym is long, but we'll be discussing that. Talking about the scenarios that we'll be running, the modeling scenarios to evaluate the different withdrawal components. And then finally, just going to go over some example model output, and this is how we interpret the modeling results once we get them. So what is the purpose of the modeling? Well, we're using a calibrated, peer-reviewed groundwater flow model to simulate the effects of groundwater withdrawals on natural systems, and those include springs, lakes, wetlands, and the aquifers, and then assisting in evaluating whether the projected water supply demands that were anticipated can be met over the 20-year planning horizon that's associated with this water supply plan update. This slide shows Central Florida hydrogeology, and the left-hand side of the graphic, you can see there's a red line on the map, and that's the location of where the hydrogeologic section goes through. So if you can imagine, if we take a vertical slice through the earth in that location, this is what it looks like. And what we see is at the top, the yellow is the superficial aquifer. It's present in Central Florida, but it's not very productive. Below that is a confining unit. And then below that, in the blue, is the upper Florida aquifer. That is the traditional source of water supply in the Central Florida area. It has been used to a great extent, and we started noticing over the last 10, 20 years that it was experiencing some stress. And we recognized that we needed to do some inter-district planning to make sure that we're not overusing the aquifer and that we're still protecting natural resources. So that's the major water supply source. Below that are some confining units, which are clays and things like that, that separate that aquifer from the lower Florida aquifer. And that is the alternative water supply source that a lot of the utilities are going to be tapping into to meet some of their future demands. And then below that is just a sub-Florida confining unit. So that's what that in a cross-section vertical slice, that's what the aquifer system in Central Florida looks like. Now we have to take that and convert that from that picture into model world, into the groundwater model. So on the right, this is the representation of that simplified hydrogeologic section on the left, and we convert those different aquifers and confining units into what we refer to as model layers. So in this particular case, we have the same basic features that's of the graphic on the right, and we converted that into a total of 11 model layers that constitute the groundwater model that we're going to be using. And it goes all the way from the superficial aquifer all the way down to the lower Florida aquifer. So I'm switching gears here to show you the surface water basins. And what you can see here is that we've got several water basins that cover the Central Florida area. The colored portion is the CFWI. I think we've shown that graphic already. And so we've got several surface water basins that cover the CFWI planning region. But what I would like you to note is we've got the different arrows pointing out the direction of surface water flow. And the next graphic, this is the graphic that shows the groundwater basins. And basically, this is the upper Florida aquifer. And what you could see comparing this slide to the previous slide is that the groundwater flows has very little to do in the upper Florida aquifer compared to how surface water flows. They're separated. In this particular case, the highest groundwater elevations are in north central Polk County, and that's why all of the groundwater flow directions are emanating from that, and they're going off radially in all different directions away from that. But just wanted to point out that in the hydrologic world, there's two different types of flows here. We have surface water and groundwater, and they kind of do their own thing. There's not a lot of interaction between the upper Florida aquifer and these surface water basins. So why are we doing this stuff? Well, we have to protect the natural systems. And this graphic is showing the extent of lakes and wetlands that are present within the CFWI planning region. You can see there's a lot of blue and there's a lot of green. So there's a lot of stuff that we need to be cognizant of and protect while we're still trying to meet the water demands of the area. So in addition to lakes and wetlands, we also have springs. And these yellow triangles with the black dot in the center of them, those represent the locations where we have major springs, magnitude 1 and 2, within the CFWI planning region, and also the rest of peninsular Florida. And we can see there are several of those springs that we need to be protective of as we go through this planning process. So I'd like to talk about some of the model history. And there really was, it's kind of an injustice to talk about this on one slide because there's a lot of work that a whole bunch of people, groundwater modelers included, actually conducted to get to where we are now, and it's been going on for quite a long time. But the first of the transient models that were associated with this area was completed in 2014. And it was referred to as the ECFT model, or East Central Florida Transient Model. Well, no sooner was that used and applied to support the 2015 CFWI water supply plan, the groundwater modeling folks that were involved with this project, we clearly understood that there were things that we wanted to do to improve the model. And we went right into that process of taking that model and updating it. We updated it with expanding the model boundaries. We improved our calibration performance. We convened a peer review panel of independent groundwater modeling experts that pretty much worked with us along the way to ensure that at the conclusion, we had a tool that the experts concurred was appropriate for what we intended to use the model for. And that was completed in 2021. It was referred to as the ECFTX version 1 model. But again, no sooner did we complete that we again recognized that there were still some opportunities for improvement. And in 2021, we took the version 1 model and we recognized that there were some things in terms of trying to get improved calibration statistics, principally in the St. Johns River portion of the model domain that we wanted to focus on. And that work was completed in 2021. And the purpose of all of these models and model updates, every time we do that, we believe that we have greater confidence in the model as a predictive tool. And every one of these times that we stopped and we did work, it was the best available tool at the time. We supported the water supply plan, but at the conclusion of that, as groundwater modeling experts, we understood that there were opportunities for improvement. So this is just presenting the model history, the evolution of the tool. And again, at this point, we think this is the best available tool that exists, and we feel confident that it can be used to support this water supply plan update. So the red is the CFWI planning region. This is a graphic that shows the extent or the model domain. So the red is the CFWI area, the blue is the extent of the model. And you can see it goes all the way from the Gulf of Mexico all the way through the Atlantic Ocean. And it is a very large area. There's over 25,000 square miles that the model covers. And we focus on CFWI, but the model covers everything. So all of the water demands throughout the entire blue area, those are all incorporated into the model in case that there were influences of withdrawals that might influence the they're in the blue area, but they're not in the red area. We still need to account for all of those things. So the model is very comprehensive in that respect. So in the upper left here, you can see just a portion of the model domain. We're using the US Geological Survey's computer code known as ModFlow. It is the industry standard in terms of groundwater modeling. What we do is we lay a uniform grid over the entire model domain, which was the blue square we showed on the previous graphic. We overlay that, and we have individual model cells or grid cells. They are 1,250 feet by 1,250 feet, so they're perfectly square. And when we lay that over the model domain, we wind up with 603 rows and 740 columns, and that constitutes the model grid. And so what the groundwater model does, it calculates all of the hydrologic processes at the center of every one of those grid cells. So it's a very comprehensive approach in terms of estimating groundwater flow and the effects of groundwater withdrawals on the natural system. So that's what we're trying to do here with this tool. We are incorporating the groundwater flow, but also all the hydrologic components, including rainfall, runoff, incorporates wetlands, evapotranspiration. We mentioned lakes, rivers, and springs, and of course the wells are the point of which the groundwater is withdrawn. Ribs are rapid infiltration basins, and that's where wastewater is returned back to the superficial aquifer and Florida aquifer system. And then there are drains that represent just features where groundwater is lost to the regional system. So this is an example of how this tool can actually incorporate all of those hydrologic processes. And again, the model is solving for those on a per cell basis. For every one of those grid cells, the model calculates the impact of those groundwater withdrawals on all of those different components of the system. So the original ECFT model, and then all the different updated versions, the calibration and verification period runs from 2003 to 2014. Calibration means that we were trying to get the model to simulate what we actually observed. That's what calibration means. And then verification is once we have it calibrated, we run it through a different period of time, and hopefully the model is able to replicate the conditions that were present in 2000, in this case, 2013 and 2014. And when it did, we said thumbs up. It's a good tool to use for the planning process. So that was the period of time. In 2003 to 2014, that incorporates both wet and dry periods. We want the model to be able to handle any kind of conditions that are out there. When hurricanes Francis, Jean, and Wilma moved through Florida, that was in 2004, 2005. Those represent really wet periods. And then we certainly had some dry periods in 2007, 2008, and I think in 2011 as well. So this period of time incorporates all of those different hydrologic features and periods of time when we have stress to the system. And we think that's a very good time period for our modeling purposes. When we do the scenarios that I'm going to be covering here, we're running the model through that same hydrologic period of 2003 to 2014 to be able to get those wet and dry periods in the system. We start out with something called the reference condition. And that is, we're averaging the withdrawal conditions from 2016 to 2020. And the last time we did it, I think we used 2014. And some people had a good point to say, 2014 was 1 year. Maybe it's not appropriate to have one single year because it could be wet and it could be dry. Maybe we should do something that's more of an average over a period of time. So we took that to heart, and the reference condition for this update to the plan is an average of 2016 to 2020 conditions. So that's the reference condition. And then what we did was we, in 5-year increments, we simulated future conditions through the system. So we accounted for the withdrawals that occurred in each one of those 5-year increments from 2025 to 2045. And those are separate model runs. And what we do is we compare the simulated water levels and flows between the reference condition and that future condition. And by doing that, we can evaluate the effects of groundwater withdrawals on aquifers and natural systems. So what we actually do is we run the 2045 scenario and we subtract out the reference condition, and that gives you an example of the difference between those two. And we do that for every one of those future conditions, and it creates a particular groundwater modeling output that we can evaluate. So I'm going to go through just a couple examples of the output that we get from the groundwater model. We have post-processing tools that take this vast amount of data and convert it into something that we as hydrogeologists can look at and figure out what the impacts are. So this is an example of one of those of outputs. And we looked at the change. In this particular case, was from the previous modeling effort that was done to support the 2020 plan. And we looked at the 2040 condition minus the reference condition. And we looked at the difference in water levels between those two, in this case, in the upper Florida aquifer, and we plotted that out on this graphic. And we at the bottom, we have a color code to determine what the level of difference in water levels between those two conditions. And so the pinkish version is showing a difference in water levels of between -3 and -1 feet. And the red areas are -10 to -5. And then the darker browns are less or are greater than 10 feet. So those are showing areas that are having the greatest influence of groundwater withdrawals on the system. So the reddish and brownish areas are showing the greatest effect of groundwater withdrawals. And then the areas that are white are showing virtually no change in difference. So what we're seeing here is the influence of groundwater withdrawals on the upper Florida aquifer. And again, this is an example of the output that we use to interpret the results and make our analysis of whether or not conditions are being impacted by the effect of those future withdrawals. So that's one way we're looking at it in plan view. And this last graphic is showing a different way. And we can look at the water levels on the left-hand side versus time. In this case that I'm showing on the screen, it was the calibration, it was the simulated versus observed, but we could just as easily use this type of a graphic to look at the 2045 minus the reference condition of 2016 to 2020. And we can look at the differences in the lake levels between those two scenarios. And again, doing a hydrologic evaluation of the impact of those withdrawals and that future condition on the groundwater system. And on the left-hand side was an example of how we would do that for lakes, but can also do the same thing with upper Florida aquifer by looking at water levels in wells. So that's the end of my presentation, and I'd be happy to answer any questions that you all may have.
We have a number of hands going up. Gabriel Milch first, followed by Angel Martin, Joseph Montemurno, and David McIntyre.
Good morning. I am very, the scenario that you presented is great, but has there been a comparison of the actual permitted allocations versus the modeling to show what actual water permits are issued versus the plan? Because I don't understand the relationship between the permits and the plan, how they cover each other.
Thank you for the question. This planning effort doesn't really focus too much on the permit side of things. This is talking about the projected demands over the planning horizon, and that's why the focus is on that more so than permits. Permit can go much larger than the 20-year planning horizon.
It's like the next questioner is Angel Martin.
Yes, thank you. I got a couple of questions. There are some newer versions of ModFlow available from the USGS. I assume you're just going to stick with the version that you started off with in back several years ago. I assume that's correct.
That is correct. The version of the version of ModFlow that was used to support the 2020 plan is the same version that we are using for this plan. Yes.
Okay. Any thoughts about trying to convert to the newer version? There are more features that perhaps can give you a little more hydrologic insight. Any kind of thoughts on that?
Yeah, I think, we just updated the model maybe 2 years ago or so, and we just didn't think that it was appropriate to go through another. I mean, as I showed on that particular slide, Angel, you've been involved on at least the latter portion of that. I think the version of the tool that we used for the previous plan was appropriate and it was updated. And I think the team will consider updates to the further versions of ModFlow from the GS for the future, but not for this particular planning horizon.
Okay, that's fine. For your new calibration, are you going to kind of calibrate using just kind of trial and error, or do you have any plans on using some sort of parameter estimation technique in order to kind of quantify your parameters other than just doing it sort of the old traditional way of trial and error?
Yeah, so we're not doing any further calibration. As I said, we're using the version of the tool that was updated a couple of years ago that improved the calibration, again, principally in the St. Johns River Water Management District footprint of the model domain. But that
Right.
effort did use PEST, the parameter estimation technique that you're referring to. That
Right.
effort did use PEST to improve the calibration in that area. So.
Okay, so there are no plans to kind of use PEST again based on some new data that may become available.
Again, not for this round of the planning process. I think in the future, we would certainly be open to doing that kind of thing when we incorporate some of the newer data that's collected, but not for this round of the planning process. No.
Okay. As you know, there's brackish water in the lower Florida and large parts of the area that the model covers. Are there any plans to try to kind of determine how much, what's the fluxes between the lower Florida and the upper Florida, especially in sensitive areas, in order to determine the possibility of brackish water flow upward from additional pumping in the upper Florida?
Again, I think the first thing we're using is monitoring data from monitor wells that are installed and new production wells that are installed into the lower Florida to help assess that possibility. From what we've seen so far in the modeling, we haven't seen withdrawals at a magnitude that would, I think we would take a look at the declines in the potentiometric surface in the lower Florida to see if there was a threat of that type of thing. But when individual permittees come in for permits, I think they, on a well field by well field basis, they are required to use tools to assess the possibility of upconing. And my understanding is whenever folks have come in for permits of the lower Florida and within the CFWI footprint, they've had to run through that analysis. And I believe each of our districts has been satisfied that is a low probability. But
okay.
But I would say in the future, just like you had mentioned, will there be a possibility of using an upgraded or more modern version of ModFlow? I think again, probably more so for the next round of water supply planning. I think it is on the table that we would consider perhaps using a newer version of ModFlow that could more explicitly accommodate that, but that's not for this round. No.
So you're treating the lower Florida as basically all fresh water. You're not considering any no flow boundary in the lower Florida based on chloride concentrations of like 10,000 dissolved solids or anything like that. So
well, we actually do. We've even though this is, as you know, just a straight groundwater flow model, we
Mhm.
try to account for the fact that at least laterally, that there are areas where the lower Floridan and maybe even the upper Florida, I'm not sure, closer to the coast, that it is of severe brackish quality. And
Right.
we specified that wherever we saw the 10,000 milligram per liter TDS interface, that is
Mhm.
considered a no flow boundary in the current version of the model.
Yeah. Okay.
So
Uh,
to answer your specific point, there are areas in the lower Florida that are so saline that
Mhm.
we have simulated them as a no flow boundary. So there wouldn't be a possibility that someone could come in and put in a lower Florida well field and the flow model would indicate a no problem when in reality there is. I think
Yeah.
by having those no flow boundaries, we're kind of accounting for that.
Okay. Yeah, that was kind of my concern with that. That would not be, because as you know, mod flow is a freshwater model. So
Exactly.
right. My last question is, your model boundaries, which are fine, they go out obviously into the Gulf, and you'll have no flow boundaries, I assume, on the western and eastern side as you did in the old model, the older versions of the models. Uh, is there any thoughts about doing any possible simulation to try to at least get an estimate of the possibility of sea level rise and its effect on the flow, especially in the upper Florida aquifer?
You know, I'll speak for myself. I don't think sea level rise is of major concern in the central Florida area. I think there could be some reduction in flow along the coast, but that's pretty far removed from the CFWI area. But again, for the next version of the plan, we are at least thinking about the possibility of using a newer version of mod flow that might more explicitly account for density dependency, in which case we could actually simulate that. But that again that's
Right,
not toward this version of the model nor the plan.
right. A newer version of the model, or a model like CWAT or something like that. They can.
Exactly. Or I believe mod flow 6 allows that for that as well.
Yes, it does. It does.
Yeah.
And I reviewed some aspects of that model. So it does account for that. So, all right.
Thank you.
Thanks.
Looks like our next hand up is from Joseph Montemurno, and if you would please identify yourself and your affiliation. Joseph, it looks like you're on mute. You'll need to unmute yourself.
Here we go. Can everybody hear me now?
Yes.
Yes. This is Joseph with the Orlando Utilities Commission. Just question on the modeling and if this is done within the hydraulic or somewhere else and with the districts as well. How are we projecting out, or how is it being projected out as far as, Angel touched on the sea level, but as far as, changing temperature, changing rainfall, just kind of climate changes and how that's being projected out in this modeling or other modeling when we're looking at this forward planning going forward? You can speak to that, Peter.
Yeah, I feel like I've said this at least a half dozen times. For this version of the tool, we are not projecting out changes in things like rainfall or evapotranspiration, but we're very much aware that the science of climate change is increasing in terms of our understanding, and we are developing tools to try to estimate what those potential changes are. And I think for, once again, the future version of the tool, we could potentially look at something like that, but there's so much uncertainty in that right now. I don't know that it would be appropriate, but I think as the science of an understanding of climate change is advancing, I think there's going to be opportunity for that in the future, but again, not for this version of the tool, nor this particular version of the plan.
Thank you.
David McIntyre had his hand up previously, then his hand went down. So David, I'm not sure if you wanted to ask a question or not. And there are no other hands raised.
Okay, next up, I'd like to introduce Doug Leeper. Be discussing the minimum flows and minimum water levels.
Okay, thanks, Pete. My name's Doug Leeper. I'm with the Southwest Florida Water Management District, and I'm also the lead for the minimum flows and levels reservation group for the CFWI 2025 planning update. What I wanted to do today is talk to you about how we're going to be using minimum flows and minimum water levels to support the 2025 planning effort. But first, I wanted to mention that Florida statutes require the water management districts or the Department of Environmental Protection to establish minimum flows or minimum water levels. Those minimum flows and levels, or MFLs, if I mess up and use that acronym, that's what I'm talking about. They're actually established or adopted by rule. By rules, that govern or dictate what the water management districts, the Department of Environmental Protection do for resource protection in the state. The statutes define a minimum flow or a minimum water level as a water level or limit at which further water withdrawals will be significantly harmful to the water resources or ecology of the area. So minimum flows and levels serve a specific purpose. They're used to identify these limits beyond which further withdrawals might be significantly harmful to the resources. So they're useful tools for all the things that the districts and the Department of Environmental Protection do, and they're useful for this planning effort. And some of the things that the districts do and the DEP does include water use permitting. Minimum flows and levels are important considerations in water use permitting decisions, not the only criteria evaluated for those decisions, but important tools for water use permitting. And they're especially important for water supply planning. And they're integrated into each of the districts' each of the water management districts' regional water supply plans, including this CFWI 2025 planning update. Just as we did before for the two previous CFWI regional water supply plans, the minimum flows and levels information factors into the planning effort through a variety of data types, including minimum flows and levels that are adopted for lakes, rivers, and springs in the area. In addition, the districts are continually reevaluating and updating and revising to improve minimum flows and levels that have been previously established. And when available, those proposed minimum flows and levels can serve as important pieces of data for the assessment of potential effects of groundwater use on our resources. As Pete went through, the ECF-TX version 2.0 model is an important piece of data, a source of data for our planning efforts. We're basically linking predictions made by that model with minimum flows and levels to determine what types of effects we might expect to be associated with demands that are projected into the future. We also use other types of modeling tools for evaluating minimum flows and levels, including surface water body models that link information provided by the groundwater model, such as the ECF-TX, to changes in water levels and surface water features, such as lakes, rivers, and springs. This is a depiction of the minimum flows and levels, or minimum flow and level related criteria or environmental criteria that will be assessed in support of the 2025 CFWI planning update. Criteria include adopted MFLs within the CFWI area. An adopted MFL established for a portion of the Upper Florida Aquifer outside of the CFWI area, but an MFL that is affected by withdrawals in Polk County, which is part of the Central Florida Water Initiative area. In addition, we will be using MFL-related criteria, including regulatory well water levels that have been established to help monitor and evaluate recovery that has been needed in a portion of the Southwest Florida Water Management District known as the SWACA, or Southern Water Use Caution Area. And then, as I mentioned earlier, the districts are continuing to revise and evaluate and update and improve established minimum flows and levels. And as they become available, those proposed minimum flows and levels will be included as environmental criteria in our assessments. This is a slide that Pete showed previously, just to emphasize again that the ECF-TX model output is an important aspect of evaluating minimum flow and level criteria for the planning effort. This slide, again, Pete showed earlier, just showing differences in or predicted differences from a reference condition to a future demand condition, in this case, the 2040 withdrawal condition from the previous planning effort, showing changes in the upper Florida and aquifer level. That type of information is helpful and used for evaluating minimum flows and levels and minimum flow and level related criteria on a site-specific basis. This is a slide similar to one that Pete showed previously, showing a time series of water levels in the upper Florida and aquifer level predicted for an area or a well, for example, near a minimum flow and level water body, such as a lake, with the black line depicting the predicted upper Florida and aquifer levels for a reference condition, and the blue line depicting upper Florida and aquifer levels through the model time period for a future withdrawal condition. And it's that difference between those two lines that's important, because that difference can affect potentially what happens on the surface, what happens to the water levels in a lake. So this is very important information that's necessary for our evaluation. And what I wanted to do now is walk you through a few slides that kind of illustrate some of the concepts we'll be using for our assessment, as well as introducing some of the terminology that we'll be using to report results from our assessment. And you can just imagine this little cube here is kind of one of the model cells that we pulled out of the ECF-TX model domain that Pete showed you earlier. And this is an oversimplification of that modeled cell. What it shows is a hypothetical cell with a lake, a water body sitting on the land surface. And the lake's full. This is a condition associated with relatively high upper Florida and aquifer water levels. In fact, we could even imagine these are totally unimpacted by withdrawals. So what we can do then is use that information from the ECF-TX model associated with those upper Florida and aquifer water levels and link it to changes that we might see in a lake in terms of changing the size of the lake, changing the depth of the lake. So that's what I've shown here. So I've shown some changes with this slide. Again, same model cell, same lake sitting on the surface, but you'll notice that in the lower portion of the cube, the upper Florida and aquifer water level has been lowered a little bit. And that's been translated to the surface, to the land surface, affecting the water levels in the lake. See, the lake's a little smaller than it was in the previous slide, smaller and shallower. This happens to be a lake where an MFL has been established. And I've identified that as with the little dot in the middle of the lake. In this case, I've shown the dot, or I represented the dot as green. Water levels have been lowered in this lake, but they haven't been lowered so much that significant harm has occurred. So I've color coded the dot for this lake green, meaning the minimum flow level for that lake is being met. So what I've shown down in the under subterranean portion of this model cell is the change in the upper Florida and aquifer water level. And I put a ruler in place as well to show that the water levels have been lowered from what they were how they were previously depicted in the slide that I just showed. And you can see that while the MFL has been met, that means there's potentially still additional lowering of the upper Florida and aquifer level that could occur before that MFL is no longer met. We call that additional lowering of the upper Florida and aquifer level freeboard. It's just the terminology we use, and you'll see it reported in our results in the water supply plan. What the freeboard means is there's still some potential lowering or changing of the upper Florida and aquifer level that could occur before a lake MFL is no longer met. And I've went out further in time when demands are projected to be extremely high in this hypothetical situation. And you can see that the upper Florida and aquifer level shown at the bottom of the cube is now even lower than it was in the previous example. And in fact, it's so low that if you look at the land surface, the lake has shrunk in size, it's become shallower. The MFL for that lake's no longer met. I color coded it red. There's been a big change in status. Formerly it was met. Now it's no longer met, coded red. Just a way to visualize this information. Changes in the lake MFLs. Associated with that change from met to not met is that lowering of the upper Florida and aquifer level. And in this case, the upper Florida and aquifer level has been lowered so much that the lake MFL is no longer met. Freeboard has gone to 0 and lower, and now we depict the freeboard as no longer existing. And in fact, there's a deficit in the upper Florida and aquifer level. So if we were to implement a strategy to recover this MFL, it's no longer met, it would potentially involve the need to increase the upper Florida and aquifer level and eliminate that deficit. So that's an oversimplification with cartoon form of the kinds of results we'll be presenting, but it's a good way to visualize the information. Status of the MFL is important. MFLs must be achieved. They must be met. If they're not met, recovery or prevention strategies are necessary. So we need to determine for current conditions and future demand projections, will an MFL be met and continue to be met? Or will a strategy be needed to ensure that the MFL is met? So we express the status, and then we can quantify that status using the freeboard deficit concept, the freeboard deficit metrics that I described. And the freeboard and deficit values of the metrics are expressed a little bit differently depending upon which type of minimum flow or level we're talking about. For lakes, surface water lakes, freeboard or deficit can be expressed in feet, change in feet in water levels. That's true for the minimum aquifer level as well, or water levels in a well. In the case of minimum flows established for rivers or springs, flowing water bodies, the freeboard or deficit can be characterized as a flow rate in cubic feet per second. Basically, how fast is the water flowing, and how does that flow rate change as a function of change in upper Florida and aquifer water levels. And then finally, the regulatory wells that we'll be using for criteria for our assessment are wells in the upper Florida and aquifer level. And again, those changes can be directly predicted in feet and change in water level elevations. This is an example from the previous regional water supply plan showing results from the analyses. In this case, it's the figure on the left shows information associated with the reference condition that was used for the last planning effort, and the 2040 withdrawals condition, again, that was used for the last planning effort. Shows the locations of the environmental criteria that were assessed, similar to what I showed you earlier. And it shows color coding, that great green red color coding that I talked about, depicting whether or not the MFL, the minimum flow level, or the minimum flow and level related criteria is met or not met. And then a good way to visualize this information beyond just color coding it red or blue, red or green is to put the freeboard values in this illustration. And that's what we did. We'll present that information in tabular form, and we'll present it in graphical form as well. So you can get a spatial understanding of where there may be potential issues in terms of whether or not minimum flow or level criteria are met and will continue to be met into the future. So that's all I have for you today. Thanks for your attention.
Looks like there are no hands up at the moment. Nope, there's one, few hands are going up now. Our first question will be by Michael Clyburn, followed by Angel Martin. And please, when you ask your question, just identify yourself and your affiliation, and remember to unmute yourself.
Thanks. This is Mike Clyburn. I'm a member of Friends of the Wekiva River. And I had a question. The MFLs for the Wekiva River are based on the groundwater conditions that are occurring in the 2014 to 2018 timeframe. And I understand that the CFWI evaluation will be based on the groundwater conditions between 2016 and 2020. So I'm wondering, when you evaluate the projects, the impact of the projects that are proposed to meet the MFL, because the Wekiva River and Wekiva Springs have been determined to be in recovery, will you be using the version that's based on the 2016 to 2020 calibration?
Hi, Mike. This is Clay Corsi with St. John's, and that's a very good question. We're in the process of developing the recovery strategy for the Wekiva Basin MFLs. It's a little bit of a parallel process as what's going on here with the water supply plan. So at this point in time, with that recovery strategy, we're planning on using the 14 through 18 average water use. But as you're aware, as we're meeting with stakeholders and discussing this, there could be a potential that we do change to a different year, such as a water supply plan 16 through 20 base year. But at least at this time, we're planning on using that 14 through 18 average water use.
If I could ask a quick follow-up question, would you anticipate any differences in the results in terms of whether the project is what the results of the project would be if you used the CFWI model versus the MFL model?
So we wouldn't anticipate any difference in results. The reason being, it's the same model that Pete went over earlier, the ECFTX version 2. The only thing that's different is the input data set for that water use that goes into the groundwater flow model.
So as far as the impact on the aquifer, it would just be the difference in the additional groundwater withdrawals.
Correct.
Oh, okay. Thank you.
You're welcome.
It looks like we have one more hand up from Angel Martin. Angel, you may be on mute.
Can you hear me now?
Yes.
Okay, sorry. My question is a little bit similar to the previous question. Question for Doug. Doug, when in the MFL determinations, you talk about the water budget models and the regional model, and many times the groundwater component to the surface water models, such as HSPF, is that groundwater component comes from the ECFTX model. And I guess my question is, when the new model is calibrated, peer-reviewed, and accepted, so the fluxes from the new model will be accepted and used in subsequent MFL determinations, or will the fluxes from the previous calibrated version of the model be used, or both?
Angel, this is Pete. So, I was trying to answer your questions, recognizing I think you raised some good points, and that, we've at least talked internally about some updates for the future, but We're not in a position right now to make a definitive decision about what future updates to the model we are or aren't going to do. That's not the purpose of today's presentation whatsoever. You know, we're trying to explain to you that, you know, we're using the existing version of the tool to support this
Right.
version of the plan. It's really premature to talk about updates to the model and then further how those updates might be used to address, you know, future questions about MFLs or anything else. We're too early in that process. And we're, quite frankly, we're really focused on what we need to do to support the 2025 update to the plan.
Okay, I was just curious as to whether the process, you know, when a new model comes in, you know, at what point does the old model stop being used and the new model starts being used? That was kind of my question. And kind of what you're telling me is we're too early in that process to
Yeah.
answer that question. Okay,
That's correct.
all right.
And there are no more hands up at this time.
Okay, thanks for your attention. Again, great questions. I'm going to introduce Kim Holtzworth, who will be talking to you about the environmental measures used in the planning effort.
Good morning. I'm Kim Ross-Holtzworth. I'm with the Southwest Florida Water Management District and the technical lead for the Environmental Measures Group. And I'm going to provide an overview of the data and the methods that the Environmental Measures Group is using for our wetlands analysis in support of the 2025 Regional Water Supply Plan. The Environmental Measures Group consists of scientists from the 3 water management districts with expertise in wetlands, surface water, hydrology, statistical analysis, and GIS. And I would like to acknowledge the hard work of this group since 2021. We've done a significant amount of work. We perform environmental assessments of wetlands and lakes, analyses of data collected from wetlands and lakes, and other related work in the CFWI planning area. And we are tasked with determining the current status of wetlands and lakes and developing tools to analyze modeled future groundwater withdrawals on wetland conditions within the CFWI planning area to support the regional water supply plan development. Our focus is on groundwater dominated wetlands and lakes that do not have established minimum flows and levels. Doug just talked about the work he leads evaluating water bodies with established minimum flows and levels. For the 2025 Regional Water Supply Plan, we assessed about 400 wetlands and lakes. Many of these wetlands were evaluated by former environmental measures groups for previous regional water supply plans. The focus was on wetland systems whose hydrology is typically groundwater dominated. In other words, these wetlands could potentially be more likely to be affected by groundwater withdrawals. We used an environmental measures group specific methodology to evaluate the wetlands and lakes, which were divided into 2 types, Class 1 and Class 2 wetlands. For Class 1 wetlands, the environmental condition and the wetland edge elevation are known, and long-term water level data are available. For the Class 2 wetlands, we know the environmental condition. There's a 3rd type of groundwater dominated wetland or lake in the CFWI planning area, and these are known as Class 3 wetlands. And there are thousands of these, and all we know about them is where they are located. We use the same methodology that was approved in the past, the same that was used for the analyses in support of both the 2015 and 2020 regional water supply plans. We spent the last couple of years going out in the field, assessing all of the Class 1 and Class 2 wetlands that were assessed in the past. This work was done from 2021 through fall 2023. We also added new wetlands when possible. For example, many of the sites being set up and monitored under the Data Monitoring and Investigations Group Wetlands Monitoring Program were added to the Class 2 wetlands data set. There was one wetland that had enough data that we could use it as a Class 1 wetland. All the field work was conducted by the same wetland scientists and their help that did the field work in support of the 2020 Regional Water Supply Plan. We also conducted a very thorough QA/QC review of all our water level and spatial data. So we use the same methodology that was used in the past to do our analysis with an expanded wetlands data set and the updated model runs that Pete talked about earlier. This map represents an example of the location and the stress status of the Class 1 wetlands data set. This is the map from the 2020 Regional Water Supply Plan, just to show you as an example. The orange crosses indicate the sites that were stressed, while the green circles indicate the sites that are not stressed. And our Class 1 wetlands data set for the current analysis includes 51 wetlands and lakes. This is fairly similar in numbers to the data sets that were used for the analyses done in both for supporting the 2015 and 2020 Regional Water Supply Plans, and includes most of the sites that were used in previous analyses. The Class 2 wetlands data set includes 27 wetlands in plain settings and 24 wetlands in ridge settings. Note that the plains and ridge wetlands are analyzed separately in our methodology because hydrologically speaking, they generally behave very differently. Our Class 2 wetlands data set includes 342 wetlands, which includes about 125 more wetlands than a data set used in the previous analyses. And as I mentioned, we visited all the Class 2 wetlands. The data set includes 208 plains wetlands and 134 ridge wetlands. This is an example map from the 2020 Regional Water Supply Plan of the stress status of the Class 2 wetlands. Again, the orange crosses indicate that they were stressed, while the green dots indicate that they're not stressed. The Class 2 wetlands data set is very important since it helps establish the baseline or reference conditions of the wetland stress status. It is large and broadly distributed, so increasing this data set is a great improvement to our analyses. As I mentioned earlier, there are thousands of Class 3 wetlands. We do not know the condition of any of these groundwater dominated wetlands or lakes in the CFWI planning area, but we do know where they are. Here's a map of the Class 3 wetlands from the 2020 Regional Water Supply Plan, and the plains wetlands are shown in green, while the ridge wetlands are represented by the purple color. As a result of extensive statistical and exploratory work, we selected Class 1 wetland water level data from 2015 to 2022, an 8-year period of record to use for our analysis. And by the way, for comparison, water level data from 2006 to 2011, which was a 6-year period of record, was used for the 2015 analysis, while a 9-year period of record, 2009 to 2017, was used for the 2020 analysis. A parameter called the hydrologic index was calculated for each Class 1 wetland by comparing the 80th percentile of water level data, which is also known as the P80, with the elevation of the wetland edge. So the hydrologic index is the difference between the wetland edge elevation and the P80 for the 8-year period of record. The hydrologic index and the stress status for each Class 1 wetland will be used to develop a statistical relationship. This relationship will be used to develop risk analysis equations to estimate the probability or risk of future change in ridge and plains wetland stress status. Using the results from the ECFTX version 2.0 model runs, these equations will predict the probability of the future change in acreage of stressed and unstressed Class 1, 2, and 3 ridge and plain wetlands on a regional scale. And what I mean by a regional scale is that this is a big picture analysis and can't be applied to the local scale or to a particular wetland. Here's some example results taken from the 2020 Regional Water Supply Plan. And the results can be summarized in tables and graphs like the one showed here in regional maps. So this graph shows the probable net increase in acres of stressed wetlands for both the plains and the ridge wetlands for different scenarios. I appreciate your time and I'm happy to answer any questions.
We have a hand up from Gabrielle Milch.
Hello, Gabrielle Milch, St. John's Riverkeeper. For the wetlands analysis, could you define what stressed means? And is that having to do with the rainfall and the time of year? Or is it about groundwater withdrawals? How do you determine the impacts? Is that something?
We go out in the field and we have a number of indicators for stress that we look for, such as examples include invasion by upland species, soil subsidence and things like that. And then after we complete our field work, the Water Management District wetland scientists get together and we review water level data and aerial photography if needed, but it's mostly the field assessment, just looking for indicators in the field.
Thank you.
Sure.
I see no other hands up at this time.
Okay, since there's no more questions, I'll go ahead and turn it back over to Callie.
That concludes all of our presentations for this technical methods workshop. Are there any additional questions for any of the material presented today? This presentation will be posted on the CFWI website, and you may find additional information there as well. This concludes the workshop. Thank you so much for attending.